Okay. What should we do in this one? How do you model? Hey, welcome back to Fat Mama Physics. In this video, this is part 2 of 3.1 modeling polynomials and like terms. So in the last video, I didn't even get to talk about what is a like and unlike term. So I hope I will get to do that in this video, but hopefully not make it too long as well. So let's get down to it. We stopped here in the last lesson and didn't get a chance to talk about modeling a polynomial. I'm going to talk about this briefly because, to be honest, I detest, that's a strong word, the ways that textbooks or nowadays how math is trying to model a polynomial. And essentially what is the basic idea is there, where you're multiplying two things, you have them in kind of like a you have it in a sort of like a two-dimensional plane, which makes sense. But I really hate the fact that when a textbook tries to model, when it tries to model X as a box of a determined side with a set size. And to me, it, as a math learner, when I remember back in the days, this was baffling. Well, not that. Well, I mean, it really didn't jive with me because it's telling me that X is determined already, and then if you really know the idea what the variable is, why can't this box be bigger? Why can't this square be bigger? Because who knows what the side length is? By drawing that diagram, you've essentially determined the size of X, or you've determined what X is. And that's not the case. It's as if you are not comfortable with having an unknown. So my way to model this is not something I can actually do on a conventional paper. I actually did something where I had to find some animations to show this one. And I may have done it also in section 4.1 later in this math series. So let's see if I can pull it out quickly just to show you what I mean. Alright, so, okay, good, this is actually working. I don't know how that's going to turn up on your screen, but right now, when I think of X, I think of something I don't know. Either a pulsating number line, which I use an arrow to show that, so it looks like this, or I think of it as a spinning die, okay? So if I have, say, a polynomial that looks like this, 3x plus 7, then if I treat one of these x's as a pulsating arrow, like a springing arrow, and since we don't know what it is, to determine what it is, you just have to pause time, and then, or that causes you to determine how long your number line is. So by pulsating, it means we don't know what this x is. It could be anywhere on this number line, and it's just constantly changing. We just don't know what it is. So 3x, meaning that the x's all have the same value. Okay, so they are all represented by the same pulsating number line, and then plus 7 actual units of whatever you want, apples, whatever, okay? And if I have something that has let's say I have 3y plus 7, then y, since it's different than x, must be represented by a different pulsating number line, because it's going to have a different value compared to x. So here, that's why I used pink, a different GIF? I think it's called a GIF. Anyways. Kids these days, you can correct me. So here we go. That's what I think would be better to represent a variable as opposed to, oh, it's a line, or it's, So then, how do we model a polynomial? Well, I know it's a spoiler here. Here I have x squared plus 7, and I didn't want to have 3x x squared plus 7. I'll have to just copy this thing 3 times, or 2 times, so I have 3 of them. But essentially what I have here is, notice that if I have a pulsating number line going out, it means that I am producing a square. And notice they're pulsating at the same time, so that if I pause time, they will create exactly a square. And we don't know exactly how big the square is because we don't know how large x is. So I prefer to use this as to model polynomials as opposed to those silly boxes that you use which have a definite size to them. And so there you go. That's x squared, and I have 7 units here. Okay. And then of course you can think about how a 3D image will look like. What's x to the power of 3? Okay, so then, okay, so that's less important. But anyways, that's how I would model a polynomial, okay? I would actually use animation. And back in the old days, I mean, they're limited in what they're able to do. Now we have technology, we had all sorts of things. There's probably better ways than my way to represent what a polynomial is. So maybe you can think of a better way to represent that. But, here we go. That is my little spiel. I'm not going to draw it here because I cannot do it. It is an animation, and an animation is the only way I believe works well, especially with you visual learners. And I know visualization is important, but it has to be mathematically sound, and that's what I value, so I'm not going to draw this here. But we will talk about what are like and unlike terms, so let's talk about that. Like terms, just like the meeples in that game, okay? Ooh, the meeples here with green, okay? Essentially, a like term means that you have a matching set of variables for when we are talking about two different terms. They have to have exactly the same variables. They have to have the exact variables raised to the correct exponent, raised to the correct power. So let's take a look at examples, okay? So for example, 5x and 3x, it doesn't matter what the coefficient is. The x and the x are the same variable, raised to the same power, therefore these are like terms. I'll just use L and U for unlike terms. Let's take a look at the next one. I have x squared, I have 2x squared and negative x squared. And again, it doesn't matter what the coefficient is. By the way, do you know what the coefficient of this one is? Negative x squared? If you thought negative 1, you are correct. Okay? So this this is also like terms. Next one, we have 2xy and minus 3yz. Okay? And you're thinking it is unlike. You are correct because I have x and y, and this is y and z. They are unlike. Very true. So that's correct. What about d? D, I have x, y squared, and y squared x. At first glance, they don't look very similar. But if you think about it, when you multiply two things, does it matter about the order that you multiply them? 2 times 3 is exactly the same as taking as 3 times 2. So in fact, I could have easily written this as x and y squared times y squared. So in fact, D, they are like terms. Okay, so D is L, like terms. Let's take a look at more examples. E, 5x squared and 3x. Now, true, they have the same variable, but they're raised to different powers. Therefore, unlike terms. Next one, F, 3x squared and 3y squared. Yes, they are raised to the same power, but are different variables. Also unlike terms. And let's keep going. 2xy and minus 4yx. Same idea as back over here in D, in which the order of the variables are swapped, but they still contain the same kind of variables. So G is actually like terms. For H, this one, we have x and y, both of them. We have y raised to the power of 2, but wait, in the second term, x is x that's raised to the power of 2, not y. So in fact, these are different. They are unlike terms, even though they have the same variables and exactly one of the variables are raised to the same power. It has to be exactly the same, just like the colors here, which... Okay, so there we go. These are like and unlike terms. And guess what? That is such an important concept in this unit because you're going to apply that in pretty much all of the sections. But to give you extra practice, let's take a look at some of these examples. So the knowing what is a like and unlike term is important when we have to simplify an exponent. So what does that look like? Take a look at A, example 2a. Notice that there are two terms that look exactly the same. You never want that in your polynomial. You always want to find a way to combine them. So how do we combine them? Maybe what we'll do is we'll do B first, okay? I'll do actually all of them, and maybe you can try D yourself. So let's do B first. So take a look at B. B looks a little bit easier because it only has x as an exponent. X as the variable. There's no powers or anything. But the thing is, all you need to do is you need to treat that batch of variables as a unit of something. Doesn't matter what. Like, it could be sacks of potatoes. It can be happy faces, apples, whatever. So if I have to translate this, then I might say I have -5 apples plus 2 apples is equal to, and you might be thinking, well, how do you have -5 apples? Fine, I could just rewrite this sentence this way, okay? But either way, I have 2 of something minus 5 of something. I'm going to be left with -3 of something, okay? I have 5 in debt. I have 2 of them to pay 2 of them off, so I'll have a -3 debt of X's in this case. Or apples, or, I don't know, Vancouver-sized homes. Hopefully not. Okay, so that's B. Let's take a look at A. A might be a little bit easier because it's an addition statement. But just keep in mind that we're going to treat x squares like, remember that batch of variables? We're going to treat that as, I don't know, what do you want? Apples, board game boxes. So let's say x squared is board game boxes. So I'll call that B, what is that? BGB? Okay, BGBs. So I have 2 BGBs plus 3 BGBs, which means I will have 5 BGBs, 5 board game boxes, and since a board game box is just x squared, I have 5x squared. So that's the idea of simplifying a polynomial. Okay, you're just putting the terms together and you're just either adding them or subtracting them as what the sentence is telling you to do. So let's go all the way to C. Okay, so first of all, you might be thinking, oh yeah, this is just -1 plus 3x. Yes, it's important to recognize that if you have a negative sign in front of anything, then you can think of that as -1 times whatever is in front. Okay, but just be careful here. Are these like terms? No, they are not like terms. They are unlike terms. Therefore, you cannot simplify this. So this, you have to leave it the way it is. No simplifying, okay? But what I'll ask you to do is maybe give D a chance, okay? Try, oh, actually, no, we haven't done that yet. So, yeah, fine. I'll do D then. All right, we'll do D together because I don't think, done on a case where there's a whole bunch of them involved. So, let's say you have a whole sentence of different kinds of terms. First of all, we have to match them. The easiest way to match them is to color code them or do something with them. So here I'm just going to start off with the 4n2, okay? And then here I have other n to the power of 2 with a negative sign in front, so don't forget to box or include that negative sign. And that's all the n squares that I have. Next up, I have the n's, just the singleton n's. This is -3n here and +5n, and those are the two I will circle. And last but not least, I have the constants. The constants are a kind of term as well, so they deserve they also deserve a particular mention. So the -1 and the -3 are both like terms, so I cannot forget them. So the next thing I would do is I would actually rewrite the sentence so that the like terms are together. This might sound redundant after you're very used to these steps, but in the very beginning, it's important to recognize what exactly what it is that we're doing. and step by step. So here I have 4n squared minus 2n. So 2n squared. So I put these two together. And next up, I'm going to do my blues. So I'll have plus, oopsie, wrong color. And sure, okay, let's say minus 3n. Okay, and then plus 5n. So these guys are done. Okay, next up I have minus 1. So don't forget your minus signs. That's important. Okay, so don't forget you still have to do those. Okay, so then after we've put them together, let's actually add the like terms, or let's add or subtract the like terms. So here I have 4n squared minus 2n squared. 4 minus 2, minusing the coefficients, give me 2n squared. Okay, next up we have blue. Okay, and I don't need to put an add or subtract, because whatever I'm going to get in my next, for my next term is going to dictate whether I need a plus or a minus. So for example, I have minus n plus 5n. This is just going to be 2n. So because minus 3 plus 5 is positive 2n. Okay, last but not least, I have minus 1 minus 3. That's just minus 4. Here we go. This is simplifying our polynomial. Okay. Woof! All right. So the math is not hard. It's just being able to recognize recognize the terms, essentially. So guess what? Maybe I'll make 4. Actually, yeah. Okay, so guess what? I think I'm gonna be done for this video. I'm gonna do one more video on, I'll do a part 3 for this one, just to keep the videos a little bit shorter, okay? So in part 3, we're gonna do a more complicated example with simplifying a polynomial, and then we have a few down here which are more like word problems. So I'm going to stop the video here. I thank you for watching, and I hope you stay tuned for part 3. Fat Mama Physics signing out.